Yes.
so odd.
I know, and then there's like your little picture. Oh, fun. That's great.
No.
Get that. I saw the little fire
I was
thing.
like, what? I don't think. What'd you do? Yeah. And I'm actually like stoked on myself right now. Yeah. I literally didn't get there.
Yeah. I'm trying to make the blood go somewhere else. I'm broken over there. I think I need to take a nap. What's happening in it?
It's just all the good vibes. One thing off the last. Yeah.
But then you're like,
Good afternoon. Did we leave off with the last time? Started to talk about, what did we leave off with, was the big thing? Eta, right, eta squared. So we'll recap that a little bit, but really important that we get that eta squared. So we defined it as eta SS between over SS total. And we called eta squared a measure of effect size. Effect size, right? It was an effect size. So eta squared is similar in respects to Cohen's d. They're both effect size measures. They're both effect size measures. So we'll recap that a little bit and continue on with analysis of variance before the break. And then after the break, we'll go over some of the assignment 2 questions, a little bit of prep for the midterm next week. Cleaning up, chapter 2. So you gotta clean up a little bit. Just talk about confidence intervals a little bit. That's part of what assignment 2 is, or filling some of those gaps. Well, what's a confidence interval? What's a confidence interval? Well, there's the formula for it, but the way for the two sample case, one mean minus another mean. But the way to think of a confidence interval is like this. So over here, I have P, that's the parameter, okay? That's the parameter. What's the example of a parameter? Let's give an example of a parameter that I want to estimate. Yeah, say like a mean, right? I want to estimate that parameter. So up on the board is the mean. Maybe the parameter, what's the parameter up here? Over here. What parameter do I want to get at? I want to get at the mean difference because this is for a two sample case, so I may want to estimate that mean difference. So we know that statistics are all about estimating parameters. Want to estimate the parameter, okay? So I stand over here and there's the parameter over there. I'd like to estimate that parameter. Well, that parameter is in the population, so I don't have access to it, right? You know I don't have access. I usually don't. When do I have access to it? I have access to it if I have all the objects, right? If I have all the objects, I know the parameter estimation is irrelevant. Still some measurement issues potentially, but estimation is irrelevant. So I see the parameter, I get, what do we call this thing? An estimator, right? I get an estimator. What's that estimator gonna be? Well, it could be the sample mean. Probably a better estimator than what? The sample median, right? Because that's the population mean. So I get the sample mean, okay? So you picture in my hand, I'm using the sample mean, and I'm gonna use the sample mean to estimate mu. Sorry, let me just go with y, because we've been using y a lot. So there's the mean of y, I'm gonna use that to estimate mu, okay, to estimate mu. We know that the expectation of the sample mean is equal to the population mean. Okay, so we know that, we talked about that a little bit. It's an unbiased estimator, it's a good estimator, and on average, in the long run, this is actually gonna get to this, okay? It's gonna get to this. However, if I take this sample mean, so imagine I got the sample mean, and I throw it at the parameter as an analogy. I throw it right at it, okay? So here's my sample mean. Going through like this here. Okay, what's the probability that it's gonna hit the parameter? Let's think about that for a second. So I've got my estimator, got my sample mean in this case. I could be a different estimator for a different situation, but in this case I'm gonna use the sample mean. So I use my sample mean as an estimator of the population parameter. The question is, what's the probability that this is gonna hit on any given estimation? Well, what's the value of my parameter? Let's give a value for it. Okay, so the value of my parameter is maybe equal to, let's just pick a number, whatever we're dealing with, but let's say 100.0. Okay, 100.0. Do you think that when I calculate a sample mean on a sample, that sample mean is going to be a match to what the parameter is? Probably not, right? Probably not. And we could even say highly probably not, right? Why? Because this sample mean, I mean, let's compute a sample mean. We compute the sample mean, say, comes out to be 98.2. Well, that's not gonna hit. Another sample mean's not gonna hit, etc. And even if I did get 100.0 for the sample mean, well, this probably has more decimal places, so I could always carry more decimal places. In other words, this attempt, almost like if I'm like throwing the spear to it like that, like that, this going through is not gonna hit. It's not gonna hit. The expectation in the long run, right, the average of all these sample means I could get is going to hit. That's okay, and this is still true. But on any given estimation, that's not gonna hit. So if that's not gonna hit, let's think about this very intuitively. That's not gonna hit. This is my estimator, so it's not gonna hit. Right there, just like that, just so we set it up here, like this. Oh, it didn't hit again, it didn't hit again. What do you suggest we do? This is too what? Too narrow. This is too narrow. What if I did this? I said, you know what? That's not gonna hit. Give it a break, right? Give it a break, do this. little bit wider, a little bit wider. Allow a little bit more flexibility in the estimator, right? In the estimator, allow a little bit more flexibility so that you provide a little bit wider of a range of values that may capture that population parameter. Does that make some sense? So I do this here. Okay, I widen it a little bit and then I throw it at the parameter. Imagine like you're estimating throwing it at it. It's kind of a good analogy. You throw it at it, then you ask the question, what's the probability that this is gonna hit? It's probably higher than if it's like this, right? So here's one example, it's coming through. Oop, caught it right there. Another one, ooh, just missed it. Another one, caught it, missed it, caught it. So then I go, wow, this is good. Producing an interval estimator, The interval is now what I'm using to do the estimation. It's not just one particular value, it's an interval. We could think of the one particular value as being what? An extremely, extremely, extremely small interval, if we really, really wanted to. We usually don't. We say that's a point estimator, use an interval estimator. Okay? You'll have a higher chance of capturing it. So let's take this to the extreme, right? I'm kind of exploring this idea and I say, wow, if I do this, I have an increased chance of capturing the parameter. Well, what am I tempted to do? I get an increased chance. Take it and make it wider, right? Make it wide, say, well, I can get the hang of this. Do this, right? It's like when you come home from work and your spouse hugs you, you got a better chance of capturing you if you're like this. Right? Nobody hugs like this, right? They'll miss you, or they'll hit you, right? So then, you know, you say to your spouse, I want to make sure I really hug you today. Right? I want to make sure. It's the same concept, right? What do? How do you approach your spouse? What would be the best way? And grow infinite arms, right? Grow infinite arms this way, and what's the probability that you capture your spouse? 100%. 100%. So it's tempting to take that interval and to make it wider. Making the interval wider is going to increase the probability of capturing what you're after, okay? So making the interval wider will increase the probability of capturing the parameter. If you make it too narrow, what happens? Eventually you get to the point estimate, and we could say that the probability that you'll actually capture kind of goes to zero because it's so narrow. As we're saying, you throw the mean at the population parameter, no, it's not going to hit. This range of values, this interval estimator, okay, so let's write that down, this interval estimator, it's an interval estimator now. Interval estimator is very common in statistics for the reasons that we're talking about, that it gives you a higher chance of actually capturing the parameter than if you use the point estimator. So we're going to call these interval estimators by the name of confidence intervals, okay? Confidence intervals. And what's a confidence interval? Well, let's use the language of probability. We've been talking about the idea of probability here. We have a lower limit, there's a lower limit, there's an upper limit, right? There's an upper limit. This is theta, this is the parameter that we're after. Okay, so theta is the parameter we're after. Different sources use different things for parameter names, you can call it whatever you want, but we just use that language theta, which is what Montgomery uses. So there's theta, and we say the probability that theta is between those two limits, right, is between the lower limit and the upper limit. The lower limit and the upper limit is equal to 1 minus alpha, is equal to 1 minus alpha. So what we're going to construct here is the idea of a confidence interval, this interval right here, that's up here, that has a probability of, what's that interval communicating? Is the probability of containing